So we have models of the atom. This is looking at several of the models of the atom. Okay, get on with it. At different times, scientists have proposed various descriptions or models of the atom to match experimental evidence available. The model that Thomson proposed was called the plum pudding model. Describe this model. Okay, you can draw a picture and label the parts, I guess. You've got a solid sphere, and you have a positive substrate or basic material with electrons embedded, or negative charges embedded in it. That's pretty much all you would have to say, I would imagine. It's really important to get the idea of the substrate. That's like your pudding, and the currants in the pudding, or the plums in the pudding, depending how you look at it, are the electrons. Anyway, moving on. Geiger and Marsden performed a series of experiments under the direction of Ernest Rutherford. It's nice to give them a little bit of recognition. Rutherford tends to take all the credit. Anyway, this led to a new model of the atom, a model of the gold foil experiment shown below. Not going to get into detail on that. As you study it, you can see exactly what's there. We're just going to get straight into the questions. Although there is one thing to point out. I think these are meant to be the various deflections and of the source of the alpha particles. One going partial small bending, large bending, and then bouncing right back off that gold foil. Anyway, B, for each of the conclusions given below, state which observation from the experiment provides evidence that A, or I, 1, semi-Roman numeral thingies. Most of the mass of the atom is concentrated in a tiny region, which Rutherford called the nucleus. The observation that matches this is that most of them, the large proportion, went straight through, undeflected or with a very small deflection. Straight through, little to no deflection. Okay, so if we were explaining that, we would say that obviously something passing through another thing means that there's empty space, and if it's striking it at a number of locations across a range, and if most of them are going through when it's striking that, that would indicate that most of that space is actually empty. Okay, next, part 2, the nucleus being positively charged. Now this one's slightly more tricky. I think there are two observations that combine for this. Here's our positive nucleus, and here's our positive alpha particle that's passing close to it. As it gets close to it, it's going to be repelled, or if it passes on this side, it's also going to be repelled. So that there's a deflection which is related to that electrostatic charge, kind of, opposite charges repelling. But it's the bouncing back that I think gives us the best clue, because if it was negatively charged in the centre, there would be you'd still get this electrostatic deflection, because you would have, say, if this was a negative charge, it would be attracted and pass around it like that. But you would expect some of them in electrostatic opposite charges, instead of bouncing right back, it would just hit it and they'd kind of stick together, I guess. Probably depends how hard they hit it, but overall the balance of it seems to indicate that you've got that electrostatic repulsion or attraction, and then the ones that bounce straight back tend to indicate that it's definitely opposite, the same charge as the alpha particle. Okay, C. Rutherford included several features in the experiment due to the characteristics of the alpha particles, and we now want to know his reasons for this. So, part 1, the source of the alpha particles is at the end of an narrow lead tube. So here is your lead, and here's your alpha particle right in there. This means as the alpha particles are going to radiate from the source of the alpha particles in all directions, the lead is going to absorb it in all of these directions, meaning you'll have a narrow beam, if you like, due to the lead absorbing, except during that narrow tube. So we would call that collimation, I believe, collimating. Part 2, the vacuum chamber. Alpha particles have a 2+ charge, so in air they will rapidly strip ions off the air, and your alpha particle will no longer be an alpha particle. It would, if you add 2 electrons, it becomes a helium nucleus, and then it's no longer doing its thing, as it can't interact with the nucleus. If you're postulating that there are charges in the nucleus and you're investigating those interactions, once it's a helium nucleus that's fired, it's not going to do its thing. And yeah, it would just interfere with the alpha particles because they can only travel a few centimetres in air due to this ionising effect. In New Zealand we would use it ionising with an S, but overseas they use a Z. Rutherford's a New Zealander, so I suppose we can stick with an S, and the rest of the world can come into line on that one. The zinc sulfide screen interacts with the alpha particle to produce a flash, plus zinc sulfide leads to flash or observable reaction, and that's the key. You can see the observable reaction, you can see where it's striking, and you can record your results because of that. And that's this question.